Okay, we're going to start section 2.7 today. I'm going to kind of take a different turn here from some of the things we've been discussing in chapter 2. This is going to bring chapter 2 to a close for us. But the topic that we're going to be discussing in this section, it's called transformations, and it tends to be something that resurfaces in just about every chapter in Algebra 2. So it's very important that you get a handle on these different transformation rules that we're going to be discussing today. As it's seemed with the last couple of lessons, today's lesson sometimes can be a little bit overwhelming the first time you're hearing all of these different rules. But as with anything, the more you practice and the more you ask questions, the easier this is going to be. Okay? So when we talk about transformations, what we're really talking about is we're talking about making some type of a change to a graph. Okay? So graphs typically come in different families. Families of graphs are simply just graphs that are displaying similar characteristics. And so here you can see this is a constant function. It would be something like y equals and just a constant. Those graphs are all similar because they're all just flat horizontal lines. Here you can see linear functions are always y equals and then x to the first power. And sometimes there's also a constant added at the end of that. But those are all graphs that are linear. Okay? And then here's another example of a family of functions. This is the absolute value function. You want to make sure that you are familiar with the fact that absolute value functions tend to take on that shape that sort of looks like a V. Okay? And then lastly here we have what we would refer to as quadratic functions. Okay? And I think that you might be familiar with equations that have x squareds in them. Those create these graphs that we call parabolas. Okay? Now, what I highlighted here in yellow for each of these graphs, we call those the parent functions for those graphs. Okay, those are the parent functions, and that's basically because it's the most basic equation and the most basic graph. When we start taking these equations and put other numbers into the equation, what happens to the graph is the graph might end up being shifted up or down. It might end up being shifted to the left or to the right, or it could even be kind of distorted and stretched. But you'll find that these shapes remain the same. Quadratics aren't going to change from looking like a parabola to looking like a straight line, or even the V graph that you get from absolute values. But transformations, inserting other numbers into the equation, will distort or change or shift the graph in one way or another. Okay? At the bottom of the front of this notes page, this really is as simple as it looks here. They're just wanting you to categorize each of these graphs based on what family of graph it belongs to. So you should be able to recognize that a V-shaped graph falls into the family of absolute value. Here we have a horizontal line that falls into the family of constant. Here's a parabola, that would be quadratic. And finally, these slanted graphs that are straight like this, those are linear. Okay, where we're going to spend most of our time, though, is actually on the back of this notes page, where we're going to be looking at how altering the equation by inserting numbers is going to make a change to the graph. Okay? So when we talk about transformations, you are making these changes to those parent equations that I highlighted on the front of the notes page. And just for the purposes of us kind of discussing all of these different rules and transformations, I'm going to use the parent equation f of x equals x squared. This would be your most basic parabola. So I'm going to have you on your calculator. If you could grab your calculator, go ahead and open up the calculator and hit y equals. I'm going to have you insert into y1 that basic parent equation for a quadratic, which is just simply y equals x squared. Okay? And we're going to take a look at this graph here together. Okay, this would be the graph before any transformations have happened to it. Now, one thing I want to draw your attention, because I know a few sections ago we were making scatter plots and things like that. Do you see how on my calculator, this plot 1 up at the top is kind of looks like it's darkened? That means I have probably a scatter plot turned on. You can just move the cursor on top of that and deselect that and move the cursor off, and that will like turn off the scatter plot. Okay, the other thing you might want to do before graphing this is we're just going to graph this in a standard -10, +10 viewing window. You can either manually do that by hitting window, or if you press the zoom button and choose option number 6 titled Z standard, it will adjust your window for you, a -10 X min, a +10 X max, and same thing for the Y's, and then it'll just graph it for you. Okay, so this is what we would call the parent parabola. Okay, so I want you to have that on your screen here. Okay, and we're going to come back here, and there's really 2 main ideas that we're going to be looking at here today. Okay, the first one that we're going to focus on is anytime, and I'm just going to kind of highlight the whole outer edge of this box, because today's lesson, the most important thing is what are in these 2 boxes here. Okay, so this says anytime you're doing something to your equation, okay, things that are occurring on the outside of your parent equation, and I'll show you what I mean by that, that is going to have an effect on your graph vertically. Okay, so we're going to use x squared as our parent equation here. Okay, and I want to first just talk about what are called translations, and these are essentially shifts. Okay, so if you were going to make a shift up, here's what I'd like for you to write down. Right underneath here where it says up, it mentions you're going to add a number on the outside. Let me just scroll so we can still see our parent equation that I put up here. Okay, right here's our parent equation. Okay, we're going to add a number on the outside. So I'm going to have you write f of x equals, and then let's just say x squared. Sorry, let me goodness. Oh, this is not cooperating here. Let's try this. All right. So we'll say x squared plus 5. Okay. You see how I'm adding a 5 just all the way on the outside, on the end of where the x squared is. Now what that should do is that should cause the graph to be shifted up 5 units. Okay. If I were to, oh, this kind of got a little discombobulated. That has to do with this. If I were to take the parent function and let's say I were to subtract 3 on the outside, well then that would cause it to shift down 3 units. So let's go back to the calculator real quick here. Okay, and on the calculator, I'm going to have you go into y equals, and I'd like for you to come down to y2 and type in the equation x squared plus 5, and then move the cursor down to y3 and enter x squared minus 3. Okay? So the blue graph is going to be the parent graph. My red graph will be the one that probably is shifted up 5 units, and the black parabola will be the parent graph shifted down 3 units. So I'm going to go ahead and hit graph here. Okay, and you can see that that's exactly what happened. Okay? So the key is, if you insert a number somewhere on the outer part of the parent function, it is going to cause a change in your graph vertically. Okay? Now, let's go back to our notes here. Okay? We're going to go back to our notes. And that's pretty easy because that kind of makes sense. Add a number, it goes up, subtract a number, it goes down. Over here is when it tends to get a little bit more confusing. Okay, on this side of your paper, we're saying now, if you make a change in your equation, but instead of just attaching the number on the outside, you put the number on the inside, and I'll show you what I mean by that. That is going to affect your graph horizontally. Okay? What do we mean by inserting a number on the inside? Okay? Well, let me demonstrate here. if you could just write down right here, let's write down as our example. Here would be me subtracting 5, but I'm now doing it on the inside of this parent function. Okay? You'll notice the minus 5 is now inside the parentheses with the x, so it's part of what we're squaring. Okay? That is subtracting 5 on the inside. Now here's where things get a little kooky, okay? When you make changes on the inside of your parent function, it does not affect the graph in maybe the way that you think that it would. See, I would think if we're talking about shifting horizontally, I would think that if you subtracted 5, that would shift the graph to the left 5 units, but actually subtracting 5 shifts the graph to the right 5 units. And I'll just give you an example that you can write down here for going to the left. I'm going to go ahead, we'll just say, let's just do x plus 5. When you add 5, okay, adding is going to make it go to the left, and subtracting is going to make it go to the right. Okay? Let's try that on the calculator just so that we can see that here. So if you could go into y equals, leave the parent function there. It's kind of nice to see that in its original position. Let's clear out the y2 and y3, and let's put in the x plus 5. Okay, and I'm just going to do that one first. Okay, this is me adding 5 on the inside. Okay, now remember we said this is supposed to make it, let me make this a minus. Okay. Subtracting 5 is actually supposed to make it go to the right. And let's see if in fact it did that. Okay, there's our parent. Oh look, this red one, I was subtracting 5, but look at the vertex. It jumped to the right 5 units. If I were to go in and change that subtraction to addition, now the graph is going to jump to the left 5 units. Okay? So it gets a little tricky here when you make changes on the inside. Here's a somewhat easy way to try to remember this. I want you to nod your head in a vertical fashion. Okay, in a vertical fashion. Okay, so if you nod your head in a vertical fashion, you should be going like this. Okay, when you make adjustments to your equation that are on the outside and it affects the graph vertically, those vertical adjustments, they make sense. If I add, it should go up. If I subtract, it should go down. Now I want you to shake your head in a horizontal fashion. Okay, so we should be going like this now. Okay? Oh, I lost my... Get this back here. Okay? So if you shake your head in a horizontal fashion, you should be going like this. Okay? Let's see if I can get this back. Right? Now, the horizontal movements, those are the ones that we would say, you know what, those don't feel like they make sense. We said when we subtract a number, we're actually going to the right. And when you add a number, you're going to the left, okay? So think, if I made that change on the inside, I better slow down. This is a horizontal movement. It's probably going to be the opposite of what I would expect. Okay, so go ahead and scroll all the way down to the bottom. I want you to look at example 2. This is asking us to describe the translation. Now, in the example that we did up above, I was using as the parent graph, f of x equals x squared. For these first two here, you'll notice there's absolute value bars in them. So for these first two problems, the parent equation is the absolute value of x. Okay? So you're thinking, this is your parent graph. Now look at how this equation differs from that. Clearly we have added a 2, and look at where it's been added. It looks like it's on the outside of the absolute value bars. Okay? So in that box up above, we said anything that happens on the outside, it's going to affect your graph vertically, and the vertical movements, those are the ones that make sense. So add, our description would be it should go up 2 units. Okay? The intention here is not for you to actually be graphing these on your calculator. I was just demonstrating that with the first couple so that you could actually see what happened. You are to just look at the equation and be able to jot down what the transformation is. Now look at example B though. Look at where the plus 3 is on this one. The plus 3 is now on the inside of this parent equation. So I need to slow down because I know when things happen on the inside, it's going to be horizontal. When we shook our head horizontally, these are the ones that don't really make sense. So if I add 3, my instincts tell me I want to say that it goes to the right, but because the horizontal movements don't actually make sense logically with what you're doing here, I really am going to say it's going to make the graph go to the left 3 units. Okay? So I'm going to jot down left 3 units. Okay, when you get to example C, you'll notice this now has a x squared in it. That's because on this problem, the parent graph, we're assuming, was back to x squared again. Okay, so you got to ask yourself, where's that minus 4? Is it on the inside or is it on the outside? Well, if it were on the inside, it would be in the parentheses with the x, part of what's being squared. This minus 4 is on the outside. That means it's going to affect the graph vertically. We would say down 4 units. Okay? All right, let's scroll back up to the top. Let's take a look at another type of transformation here. Okay? Another type of transformation called a reflection. Okay? And we're still going to just use f of x equals x squared as our parent function. Okay? So for reflections, if you were to multiply on the outside of your parent function by a -1, that is going to cause the graph to be flipped across the x-axis. Okay? So how might that look for f of x equals x squared? Well, here's my parent function. If I'm going to multiply by a -1 on the outside, I'm just going to place a -1 right out there in front. Okay? If we were to graph this, what you would see on the calculator, you would see the parent graph like this, and then you would see the reflected graph look like that. It would be flipped over the x-axis. Okay? If it's flipped over the y-axis, well, now you're multiplying on the inside by a -1, and that's going to cause it to be flipped across the y-axis. Okay, so how might that look in the equation? Well, I'm going to now put parentheses, and inside those parentheses with the x, I'm going to put a -1. Okay? Now, if you actually graphed this one, you would see the parent graph would look like this, and then the reflected graph would go right over top of it. Because it's being flipped over the y-axis, it's symmetrical here. What's on this side would go on that side and vice versa. Okay, let's look at a couple examples involving reflections. Let's look at example 3 here. Okay, in example 3, it's asking us to describe the reflection. This is one that we just did here. You got to ask yourself, where is that -1 being multiplied? Feels like this one's on the outside. Feels like example C here, that's on the inside. Okay, when it's on the outside, that's when we say, okay, when it's on the outside, this is when we're saying that it is going to be, oh goodness, this is not cooperating here. This is going to be a flip over, and this is a flip over the x-axis, whereas this one is a flip over the y-axis. Okay? This one is switching to the absolute value as the parent function, so again, you got to ask yourself, where is that -1 being multiplied? Well, it certainly looks like it's sitting on the outside of the parent function. So we would say that this is going to be a flip, or you could use the word reflection, over the x-axis. Okay. All right, so let's look at the last type of transformation. This is definitely the most difficult. These are called dilations, but they're also referred to as your stretches and your shrinks. Okay? So I use little smiley faces down here. If you guys have ever inserted a piece of clip art into like a Word document or something like that, and then you want to make it bigger or smaller, you kind of have to grab it at the corner in order to do that. If you grab it at the sides or grab it at the top or bottom, it tends to distort the picture. Well, that distortion is what we're talking about when we talk about a dilation or a stretch or shrink having occurred on your graph. Okay? So here we have a vertical stretch. Okay? And the vertical stretch is any time you are multiplying on the outside, where we said vertical things happen on the outside, but it's got to be by a number that's bigger than 1. Okay, got to be multiplied by a number that is bigger than 1. So let me give you an example that you can write down here. Oh, gee. All right. So we can write down f of x equals, and then I'm going to put any number greater than 1 on the outside of our parent equation x squared. Okay? This would be an example of what we would call a vertical stretch. Okay? The bigger the number, the higher the stretch factor. So we're going to call this a vertical stretch, and then you always have to say what the stretch factor is. You can just put SF for stretch factor. The stretch factor is 4. Okay? It will become more elongated and more stretched out vertically the higher that number is. Okay? When it comes to vertical compressions, this is when you're multiplying on the outside, but you're multiplying on the outside by a number, like a fraction that's between 0 and 1. Okay? Also, another word for compression is shrink. It would be okay to call these vertical shrinks. Okay, this is like coming at the graph and you're kind of coming at it vertically, but you're compressing it and smashing it down. It has this effect. Okay, so now I'm going to show multiplying on the outside by a fraction between 0 and 1. Okay, and I would call this a vertical shrink, and I would say that the shrink factor is 1/4. Okay, the shrink factor is 1/4. Okay, all right, now that was fine. That kind of feels like it makes sense. If I multiply by a big number greater than 1, it's going to stretch it. If I multiply by a small number, a fraction between 0 and 1, that's going to shrink it. Remember, the vertical transformations, those are the ones that feel like they make sense. Things get a little crazy when you come over here and now you're multiplying on the inside. Okay? This is the opposite of what you would expect to happen. Okay? When you multiply on the inside by a fraction between 0 and 1, and I'll have you write this down as your example. Okay, so now I'm going to go inside the parentheses with the x here and put the 1/4. What this actually does is it actually grabs the graph on the left and right and it stretches it out horizontally. So we would call this a horizontal stretch, and here's where you got to be careful. The stretch factor is not that number. The stretch factor is the reciprocal of that number, okay? And that is also the case over here when we talk about the shrink or compression factor, okay? All right, so finally, when we talk about horizontal compressions or horizontal shrinks, okay, this is when, again, we're always on the inside when we're a horizontal transformation, okay? Only here, we're multiplying on the inside by a number bigger than 1, okay? So now I'm multiplying by 4 on the inside. I would call this a horizontal either compression or shrink, and my shrink factor is the reciprocal of 4, 1/4. Okay? We're going to try a few of these here, and then we're going to bring this to a close here. I know this lesson is a little bit longer here. Let's try example 4 here. Okay, you can see that you got to ask yourself, where is the number? Because if you can categorize it on either being outside or inside, then you've narrowed down whether it's affecting the graph vertically if it's on the outside or horizontally if it's on the inside. Okay? Now, if the numbers are being multiplied, those are your stretches and your shrinks. If the numbers are being added or subtracted, those are your shifts, up, down, left, right. Okay, here we have a 1/4. It's being multiplied, okay? I say to myself, but where is it being multiplied? It's being multiplied on the inside. So I know this is going to be horizontal. It's either going to be a horizontal stretch or a horizontal shrink. Okay, I kind of need to go against my instinct here. When I see fractions between 0 and 1, my mind wants to say it's a shrink. But if it's on the inside, I need to go the opposite of that. I need to do horizontal stretch. And my stretch factor is the reciprocal of 1/4. It's 4. Okay, on this next one, you ask yourself, where's the 2? The 2 is on the outside, so now this is going to be something vertical. The vertical ones are the ones we said that do make sense, so when you multiply by a number bigger than 1, that is going to cause it to stretch. So vertical stretch, stretch factor is the exact number you see there. You only do the reciprocal things when it's horizontal stretch or shrink. Okay? Here we have a 1/3 multiplied on the inside. I'm going to call this horizontal. It's a fraction, so my instincts want to say shrink. I should go against that and say stretch, and I'm going to say the stretch factor is the reciprocal of 1/3. It's 3. Okay, and finally, even though this 1/2 is in parentheses, look at where it's at in relation to your parent graph. It is on the outside of the absolute value bars. So this is definitely going to be vertical. Okay, I just erased that. Okay, great. Okay, so it looks like this was the equation that was there that I just erased. We're going to call this a vertical shrink, and the shrink factor is 1/2. Okay, I'm just going to pick 2 of these at the bottom to look at with you, because really what is going to happen on most of these problems is they're going to throw multiple transformations at you all at once. Okay, so let's just take a quick look at example A, and we will take a quick look here at example D. We'll just do these 2 here. Okay, so again, what I like to do is I like to pick out everything that is on the outside and address all of that first. It really doesn't matter the order you do this, but that way your brain is kind of staying in the same vein. Everything on the outside is vertical, and all those ones make sense, and then when you address everything on the inside, then your brain is doing everything horizontal. Okay, so this 4, it's on the outside, it's multiplied, so that means this is going to be a vertical. I'm going to call this a vertical stretch because the 4 is a number bigger than 1. My stretch factor is 4. Okay, then I see that there's a minus 25 at the end. That's also vertical, but it's just a vertical movement down 25 units. Okay, now I'm going to go on the inside. I'm adding a 2.5 on the inside. Okay, adding and subtracting, those are my shifts. So it's either going to make it go left or right. I should choose left. I'm going to say left 2.5 units. Okay, down here, example D, see this little negative sign in front? That means we're multiplying on the outside by a -1. Okay, if you multiply on the outside by a -1, those are your reflections. Outside by -1, that's a flip. Remember, on the outside here, by -1, that's a flip across the x-axis. The other thing that's happening on the outside is that -3. That's going to be down 3 units. And then the 5, that's on the inside. That should be a horizontal shrink of 1/5. Okay, my shrink factor is 1/5 there. Okay, that's a lot. You can rewatch parts of this video if you're not sure, and please reach out if you have questions.